Thank you so much for the introduction. And thank you so much for giving me the opportunity to talk today. I think it's a wonderful meeting. And it's quite exciting to speak in the barrier session. It feels like going back to when I was at the VIS, and I was always kind of the barrier to all new experiments. But that's history now. Yes, for sake of time, I start with the acknowledgement slide, so we don't miss thanking anyone. Okay, now I see actually that the presentation was not really updated. No matter, there's a lot of people here today that I want to acknowledge for some of the work. So I want to start with Don, of course, but also mention Ben, Maus, and Tayun, that will luckily speak after me, so that's easily, and Andries van der Meer, he's also here. And then, of course, acknowledge my own group now and funding. So I focus a lot on engineering the neurovascular unit, and that's an excellent barrier to start with. And when you talk about the barrier, then often we talk about the blood-brain barrier. So what we are interested in there is, of course, understanding how the neurovascular unit controls drug penetrance. That's one reason, but also generally how it controls brain homeostasis, and how it's affected in neuropathology. And I mean, a quick review what it looks like. We all know that, you have a capillary with endothelial cells and circumvented by pericytes and astrocyte end feet, and also outreaching neuron processes. And we worked with a couple of variants of how we want to model the neurovascular unit. And I've helped classify them a bit in our 3D approaches. Oops, sorry. Let's see if we can get this pointer. 3D approaches, where we have a monolayer of endothelial cells lined with different perivascular cells. These are very interesting for studying cellular interactions, but they can be a little bit more difficult to get perfectly reproducibles. And me and Andries did a nice study there back in 2016. Today we'll talk a little bit later about the study that we more recently did, where we have a more controlled way of designing where we create the 3D-dimensional model. For more quantitative approaches, we approached the way of doing more this 2D layered chips, often now recognized more like the VIS layout of chips. And I will describe today a little bit about how we did a new model of that with a material that easily integrates multi-materials in one fabrication steps. But if we go back how we started on this, and when we were at the VIS some years back, we had the task to model neurovascular units. And we actually at that time started thinking how we can get more data out of it, of each part of the unit. So we disintegrated it into different kinds of units that we could sample individually. So you on Zoom, it won't be so easy to see what your point, but what we did then was disintegrating neurovascular units into 3 chips. So one blood-brain barrier, one more brain chip, and another blood-brain barrier that were connected through their secretome. So you have the mimic of the bloodstream here, and then the connection through the secretome. And the chip layout, you have the beautiful cartoons, but then you have the chip layout looking something like this. And what we did then was, of course, what we all have to do with a different kind of musculoskeletal systems that we do. We had to validate it for human characteristics. We could see that the response to certain drugs, with alternating the barrier function, we can look at different penetrance of drugs, and also cellular interactions. At that time, we worked all with primary human cells. And what we have been working much more in my lab after that is actually transition this to more IPS-derived systems. Simply because we want to be applicable also in industrial setting and to be scalable. So I don't have to introduce induced pluripotent stem cells to this audience, I think. So we kind of skip that slide. But just to have something that we can get an unlimited cell source that can be applicable in wide settings. So the different kind of cells that we work on mostly when it comes to neurovascular units is, of course, the endothelial cells and the glial cells and the pericyte cells. We also do work with neuronal cells, but I won't go into them today. So when we start thinking about iPS-derived cells for the endothelium, we back then in 2018, in a collaboration with AstraZeneca, did a comparison between two major protocols. One more, the Wisconsin protocol, as I call it, and the other one more, the protocol that was from Leiden University. And in our hands, when we worked with those two protocols, our ideal what we wanted in brain-like barrier function. And our two metrics that we compared was the transendothelial resistance, and if you take the Wisconsin protocol, that is the protocol 1 in the slide, and the other protocol is protocol 2. And we could see that the barrier function was much higher in the protocol than the Wisconsin protocol. And when we wanted to compare apparent drug permeability, this was the only protocol that actually could discriminate CNS penetrating drugs from non-CNS penetrating drugs. And that was our motivation to continue with that protocol. And what we did then was actually, or a study that was done mostly by my colleague here, Tayun, and I will just highlight one thing that I thought was very interesting with this study. It was that we took this Madison protocol, it was improved by hypoxia treatment, and we looked at if we can discriminate transcytosis rates with this protocol. And we used a well-known system, the transferrin receptor targeting antibodies, and compare the transcytosis rates between one antibody that is known to penetrate the blood-brain barrier and one that actually gets stuck into the cells. And thanks to this improved endothelial protocol with hypoxia, we could actually, on chip, on a blood-brain barrier-like chip, we could discriminate these two antibodies with real-time analysis. And in this chip, what we had was then this improved endothelium, but the rest of the cells, the perivascular cells, were actually primary cells. What we have done now lately is actually continuing looking at different kind of transcytosis processes with a variant of this endothelial protocol, the accelerated protocol published by Neil 2019. And so we have done a number of different transcytosis studies, but this is one where we used lipid nanoparticles. They were coated with chondroitin sulfite, and also they had a blood-brain barrier penetrating peptide from the TAT sequence, which is HIV derived. And when we did that, those nanoparticles had previously been shown to be strongly anti-inflammatory in the brain. And when we conjugated them with this TAT derivative peptide, we could see that there is no impact on the barrier function. These nanoparticles keep the barrier intact, but we could strongly see that we have it conjugated with the peptide, we have a much higher penetrance than if we have it non-conjugated nanoparticles. And you can also maybe see the red dots here in this endothelial slide, whereas we don't see it here. So also this endothelium can support this transcytosis mechanism, which is actually debated what kind of mechanism that's going on there. And we could also not single out one transcytosis mechanism that was dominant, but that's another problem. Still, this endothelium supports the transcytosis. So that was kind of our validation of this brain-like endothelium. But it comes to the other cells then, and I will describe our astrocytes. So we have been working since long back to get scalable and functional astrocytes from iPS cells. And our general route is that we take the iPS state, and then we derive a stable neural stem cell state that we can actually pass it for over 100 passages without the large drift of the neural stem cells. And then we have done a couple of different protocols where we derive astrocytes from them. And just very recently, in a month ago or so, we published this paper, which is a very simple protocol. If you follow it, it's just an astrocyte growth supplement that you give to the astrocyte during 28 days. And then we get a strong upregulation of astrocyte markers. We don't get upregulation, of course, of neural markers. We got a strong expression here of 3 lines. We show astrocyte markers stably expressed. these astrocytes, as it's not only the markers that you need, they're also have a strong inflammatory capacity, and both with IL-6 and IL-8, and also ICAM expression of inflammatory stimuli. And interestingly, they also have a very nice glutathione synthesis and secretion, which is actually on par or even better than if we compare with fetal primary astrocytes. And now when we have all these components, we recently integrate them together in a new barrier chip, which was made in a one-step injection molding as a material called off-stoichiometry thiolene epoxy. The beauty with that material is that it has both epoxy bonds and thiolene bonds. So when you do the injection molding, what you actually can do is that you can integrate materials like a good bonding of metals or a tracheous membrane, in this case of polycarbonate, into the membrane directly. So to monitor the barrier here, we actually did impedance-based barrier sensing, as opposed to the conventional tier. The electrodes are just integrated on the membrane. You can select your own frequency that you're interested in, but we went somewhere in the middle there where we could monitor both tight junctions and a little bit of capacitive cell attachment. And we went about to study this model because we know one caveat with that endothelial protocol is that it doesn't actually support inflammatory processes very strongly. So we looked at how much it supported stress processes, and this is specifically neutrosative stress, where you kind of mimic microglia activation through a compound called SYN1 that degrades to peroxynitrite. And what you see there is kind of individual barriers that are formed. You see they're not all the same. You see there over those little spikes, that's when we do media changes. And when we then challenge it with this stressor, the SYN1, we can see that the barrier is responding to it. So this kind of stress, this endothelium is responding to. And we could also see that it was sensitive to a prophylactic treatment with a clinically relevant antioxidant called NACA, which actually then can save the barrier from this stress. And it was interesting, since we have the astrocytes there supporting glutathione pathways, we actually could see that actually there was a clear glutathione activation in this case. So I want to kind of quickly remind everyone about a small thing, was a publication we did last year. When we talk about barrier system, a lot of people tend to show these beautiful slides and just show the ship, and then you discuss about, okay, the ship must not be absorbing certain molecules either into the chip or on top of the material. We recently did this study to kind of validate how much does it matter. So we tried to do it in a totally realistic organ-on-chip prototype setting. And then many people just concentrate on the chip, and they don't really set up the whole model as it is. So, oh, sorry, this was where my slides weren't updated. So what many people do is, of course, they just look at the material and look how much absorption there is in it. But what we did was actually setting it up in a peristaltic pumping. And it was very clear, of course, it depends on what kind of surface area you have, your chip to whole system area. And I just want to raise the issue of the take-home message of our study is like, be really careful what tubing you use in your prototype systems if you want to do any drug studies into them, and avoid most kind of soft tubings. Then, of course, it's very interesting what material your little chip is also made of, but of course it relates to the surface area of the whole system. And I want to then quickly switch over to our last system of 1%, going back to the 3D models. Previously, where we worked with something called, where we did kind of a fingering process to generate lumens into gels. But we recently developed a method to do kind of direct laser writing, where we use a femtosecond laser that creates not actually ablation of material, but because of its intensity and very fast pulse repetition, we can get air bubbles or bubbles into the system that pushes the gel material that you have in your system to the sides. And that is actually an extremely gentle process. So what you get in that system is that what this slide shows here is that we actually printed our lumens just next to a glioma organoid, and it wasn't damaged at all. We also quantified actually damage to the side. Thanks to this really, really high intensity but fast process and just a kind of bubble formation, we can create this vascular where we want it around organoids, which we recently published. Okay, we skip that for sake of time, these videos when we do this. So anyway, I want to finish up the talk with just, again, emphasizing two things. One is we really need to improve our chips in many ways. One is integrated sensing, that I think is one thing, and then the integrated systems that many of us are describing. And the other one is to continue improving the cell sources that are needed. And typically, these must be iPS-derived cells. And with that, thanks for your attention. And again, thanks to all the people contributing to this work.